Okay, good morning or good afternoon, depending on when you're viewing this. Hi, my name is Art Cho. I'm the CEO of inCerebro, and this is an introduction to my company. Well, first of all, the name of my company. Some of you might have guessed what that meant, but I'm sure if you are especially English speaker, that cerebral might have come from this word cerebral, which means your brain, basically. So it actually is a parody to the following. You know, in drug discovery, we have experiments doing in vivo or in vitro, right? I mean, in vivo means that you're doing it with live animals, and in vitro means that you're doing these experiments in a test tube. But just about 30 years ago, people started using this term in silico, which means that you use the computer programs and do the research to do the drug discovery. And I've been doing the kind of research that's relevant in this field for the last 20 years or so. And then one thing I realized that these programs are not just like a black box. I mean, it's not as easy as just pressing the button and everything will be taken care of. And there are a lot of different kinds of programs and a lot of different levels of theories that you really have to think about, and you use your own judgment to do the right kind of simulations and research for the drug discovery itself. So I started thinking about these terms in cerebral to mean that okay, when you do the in silico experiments, you have to have another level of thinking about the problems, and that will make a whole lot of difference there. I've been using this slide actually since 2007. Use it as a sort of an icebreaker here and there in the conferences, and some people actually recognize the word I see. Anyway, that's the story behind the name of my company. Okay, moving on. So that actually sets up the idea about the identity of my company. Our motto, as you see here, is from the mind come drugs of the future. So we're emphasizing on the fact that we had to think about these problems before we started using computer programs. But in actuality, what happens is that we need the kind of technology that's related to computers and computations. And now I can say that we're basically using the combination of molecular modeling techniques with the power of artificial intelligence, which we call AI these days. In particular, for the molecular modeling, we use the quantum mechanical calculations for accurate predictions, and that's one of the things that we show as our expertise. Okay. Well, so moving on, I'm gonna tell you a little bit about my background, and that can explain quite a bit of what my company represents. Okay. I was actually educated as a physicist, so I have my PhD in physics, but as a postdoc, when I was doing a postdoc doctoral work at Caltech, I started working on the simulations of biomolecules, and I developed some programs that can be used in drug discovery. I continue on in that line of research at Columbia University as a research scientist, and there I met Professor Rich Friesner, who liked my work so much so that he hired me at the Schrödinger. By the way, Rich Friesner is one of the co-founders of Schrödinger. The other one, by the way, being Professor Bill Goddard at Caltech, who was my postdoctoral advisor. In any case, so I worked at Schrödinger for a couple of years in developing this program called QPLD, and that became one of the flagship programs of Schrödinger. And with that kind of an experience, I started to work on the development of these programs and methodologies that's relevant to drug discovery. And that's where I had this idea of founding the company inCerebro. So I can tell you that my root is firmly based in physics, but I also have an experience in how to apply these computational methods to drug discovery problems. So our strengths can be, thought of as having some of these computational the methodologies that's used basically nowadays quite widely, but I improved upon those things. For example, Schrödinger has this program called WaterMap, and that's one of their flagship programs there. And I guess the Schrödinger, when they first developed the WaterMap, it wasn't really related to the power of AI at all. But now, through the years, I collaborated with Professor Tom Korsman, who was my colleague at the Columbia University, who is now at the CUNY. We collaborated on the development of what we call water pharmacophore. It's actually some kind of an improvement of WaterMap, I would say. And now with that technology, we were able to apply AI. And in fact, at the end of it, we could work on the development of first-in-class drug developments that's based on what we call an active learning. So let me just tell you that our drug design platform. It's called the MIND. It's an acronym for Modeling with Intelligence for Novel Drugs, and it consists of the three axes of these technologies. One is called active learning. Another is called water pharmacophore, which I just touched on in the previous slides. And then there's something called QMM docking. So that's where I use extensively the calculation using the quantum mechanical theory, and use that for the evaluation of the drug compounds and so on. Okay. I'm not going to get into all the details of these technologies, but let me just briefly describe the two of these core technologies. One is water pharmacophore, which I talked about in a couple of slides earlier. It's akin to WaterMap of Schrödinger. This is what the WaterMap outputs on the screen, and what we have is sort of a simplified picture of what WaterMap can show you, but we call this water pharmacophore, and as you can see, it kind of resembles some kind of molecules that might bind this protein target. And in fact, our intention was to come up with all the calculational facilities that will generate this kind of uh, the basic frame of the molecules that can be used as a drug compounds for this particular target. And that's actually, although I'm not going to get into any more details about the whole process, but what we did was to marry this technology with the power of AI, which will give us this method that's called target-specific drug design methods. And that's based on the deep learning and water pharmacophore. Of course, deep learning is like the most well talked about the methods for the implementation of AI, and we developed these methods and published it just about a year ago in this journal JCIN, which is published by ACS. Okay. Anyway, so moving on, this another part of our core technology of the platform mind is called QMMM docking. Okay? QMMM docking it's based on the quantum mechanical calculations, and you might have heard of what quantum mechanics is and all that. And the only thing I want to point out at this point is that yes, if you apply quantum mechanical calculations, you can get a better accuracy. The problem is that the quantum mechanical calculations take a lot more time. So it's our own technology that we have this specialty in how to apply this quantum mechanical calculation so that the whole calculation time is doable. And so what we do is to find these little differences that might come from the quantum mechanical calculations that you won't see from the molecular mechanics, which is like a conventional way of doing the calculations at this level. So our methods in general gives higher accuracies, and we have proven that with some of our research published in numerous papers. So, in summary, our technology can show you some of the unknown ligands that you can derive from just knowing the structure of the protein target, but at the same time we can calculate very accurately how these compounds bind the drug target. So in fact, what I would say is that our technology is what I call the quantum ready. Okay, quantum ready. I'm saying this meaning that our methodologies are well proven using the quantum mechanical calculations, and in fact, as I said earlier, that when I was working for Schrödinger, I developed this program called QPLD, which is still the only commercially available QM-based docking program in the world, and that was basically my own project, and as I said earlier, that I improved upon this methodology after I left Schrödinger and started working for Korean University, and in my research group we did numerous publications to prove that we can in fact improve on what the QPLE can do. So we'll still continue to work on this line of research, and I can tell you that although you probably know what quantum computer is, you've heard this term as the next big thing in the technology. But in any case, we were getting ready to be able to apply quantum computers when it becomes practical, although it's still in its infancy in technology development. Anyway, now finally, I'm going to show you the examples that we've done as a collaboration with other firms. For example, this particular target is DNA binding protein, and we're developing the drug for the colon cancer treatment. And out of 5 million compounds, we selected 200 using our methodology, and we tested 81 purchasable compounds out of those 200, and eventually we had 3 compounds at nanomolar level activities with 14 compounds at micromolar level activities. Well, which I would say is an excellent result. These are like and representative examples of what you can do for a drug screening using the virtual platform. We can do more than that by doing the de novo drug design using our Mind platform, but that's something that I can tell you that can give you an excellent result if you want to collaborate with us. Okay, so I think that's probably enough for introduction. So I appreciate your attention, and thank you very much.